All right, cool. So just so you guys know, we're recording right now. So I want to just do like two problems with regard to electric potential today. And then I want to get right into circuits, because circuits are the part where it actually gets interesting. There's just a few things that I want to write in terms of like notes. Let's see if we can do this. All right. So you guys remember that the formula that I gave you for electric potential? Well, hold on. Let me ask one quick thing first. You guys remember what this says? So conservation. All right. So you guys, I believe in DP Physics 1. You guys talk about conservation of energy. Yeah. Yeah. No. All right. So if you don't remember what conservation of energy says, okay, it says that if you add up all of the energy within a system, so if you add up something's kinetic energy to its potential energy. Now, I'm going to write a little G next to this. So this is like, remember we said use U, don't use P, like don't use PE. So I'm going to write this as gravitational potential energy. So if you add the kinetic plus the gravitational potential energy, and I'm going to add another term here. And this is where like you're going to be like, oh, stop using U. All right, use a capital U. So we're talking about electric potential energy. Okay, we'll abbreviate that with a lowercase capital E for electric potential energy. So if you add up all of the energy within a system, it should be constant. That's what the conservation of energy says. Assuming that no energy is lost due to friction, heat, or other forces. And you know, like this is a good approximation. Now, what this means is the total energy that you start with equals the final energy, all right? So now, you guys, there's a little side note. So I don't remember if you guys did this in DP Physics 1, but what's the weakest force in nature? Gravity. And what's the next? There's two ways to ask the same question. What's the next strongest force or the next weakest force? Like what? Go ahead.
The weak nuclear force? Electric force.
Yeah, so the electromagnetic force. So I'm just going to write E and M force. All right. So gravity pulls you down to the earth. The electromagnetic force prevents the atoms in your body from going through the floor. Like, all right, it's the opposite, or sorry, like charges repel each other, right? That's the electromagnetic force. What we're gonna talk about this year, sometimes it's good to think about the electric force, the force between charged objects, like charges repel, opposite charges attract. Yeah, that's a good way to think of like the electric force. But then there's the magnetic force, the thing that keeps, for example, this eraser attached to the wall. It's got a magnet in it, and this board is magnetized. Now, these are the same force. It's not like there's two different forces. They are identical forces. They just manifest themselves. They just appear in slightly different ways. Then there was the strong and the weak nuclear force, right? And these are both nuclear forces. You and I will never experience these directly, right? Well, we sort of do, but not really. You have to go to like a nuclear power plant where you smash atoms into each other to see these forces happening. But just to clarify, weakest, next weakest, and then these two get strong, right? These are the forces responsible for keeping atoms together, all right?
Why can we like feel gravity and electromagnetism?
Why can we feel those?
Like, why can we feel the weak ones and not the strong ones?
That's a good question. So like, let me ask you guys this. So we're here on Earth, and Earth has a certain gravity. What would happen if you were to go to the largest planet in our solar system? So if you were to go to Jupiter, and I don't think I can draw it to scale. Jupiter is something if I remember, Jupiter is like 400 times the mass of the Earth, something like that. Like what would happen, assuming like, so this is Jupiter. Assuming there was a solid surface to actually stand on, if you were to go to Jupiter, do you know what would happen to you almost instantaneously? Yeah, you'd be crushed by your own weight. And the interesting thing is you'd be like, wait, but there's no solid surface to stand on. What would happen if I were to take you and then bring you right down to the bottom of the ocean in a submarine and then just push you out? You'd get crushed by the weight of the water above you. And in a similar way, you'd be crushed by your own weight here. And if you were to actually go down into Jupiter and assuming all of the different crazy forces besides the tidal forces didn't tear you apart, yeah, you wouldn't last long here, basically.
How do you weigh your planet?
Well, you don't, so like, yeah, that's a good question. We don't weigh planets, we find their mass. So like if we know them, like, so for example, maybe we can talk about this in greater detail when we get to circular motion. But so everyone knows like the sun is a star. The really interesting thing is one of the ways that we can detect at what are called exosolar planets, planets that revolve around other stars, is we can measure how much they make the star wobble. So like a big planet like Jupiter, yeah, like if you think of it as like this is like a terrible way to do it, but like imagine this. All right, gravity's kind of like a string, so I'm gonna just do it this way, just so everyone can see it. Gravity's kind of like a string, right? Or a rope or a chain. It keeps things from flying away, all right? And imagine that the mouse is Jupiter. And like, you know, where my hand is holding, imagine that's the star. So as like Jupiter revolves around the sun, it's gonna pull the sun a little bit as it goes. And it causes the star to wobble back and forth a little. So when we look at other planets, we can detect that wobble. We actually have better ways now. Like that was like one of the first ways that we detected exosolar planets. But we can get a good sense, actually a very accurate sense of the mass of different planets, depending on how much they make the star wobble. So the bigger the planet, the more it causes the star, or in this case, the sun, to wobble. Yeah, so this was like this is like a side note. The reason I wanted to ask you guys this question here is we're dealing with electric circuits, okay? So we don't need to think about the gravitational force anymore. We don't need to think about gravitational potential energy unless it's a very big thing. I think one of the problems that I gave you was you had like a ball with a certain charge on it. Like that's a different, like you need to take gravity into account in that case. All right, so all right, so I just want to look at that. So was it problem 3? It says an electron in a cathode ray tube is accelerated from rest through a potential difference of 5,000 volts. What is the change in the electric potential energy? So whenever you see this, whenever you see electric potential, think electric potential energy, okay? Did you guys get this problem?
Yeah.
Yeah, no? Yeah?
This was the one with the electron in the tunnel?
Yeah, so like in the cathode ray tube, so like you have like if you think of this as like you have 2 plates. So one of the plates is positive, one of the plates is negative, and then like, you know, maybe you have like an electron like this, right? That's our symbol for electron. So like you have electric potential energy, delta U capital sometimes. I think we wrote this. We might have just wrote this as delta or U. What was on this side? Can you guys tell me what was on this side of our equation? Q. Yep, so this is your voltage, all right? This is your electric potential energy, right? For this being an electron, what's the charge of an electron? 1.6. Very good. So like for that first one, I think this is what, A? Yeah. So 1.6 times 10 to the negative 19. And this would be coulombs, right? And so this would be times, this one said what, 5,000 volts? Yeah. Just to recap something that we said in the online lecture, a volt is a joule per coulomb, the energy per charge. So that's why when you multiply volts times coulombs, you get units of energy. What did that work out to be as a number? 10 to the negative 16? And what are my units on that? And then the second part was, what is the speed of the electron as a result of this acceleration? Okay. Here's why I put this formula up on the board, like your conservation of energy, okay? So I'm going to just erase this. All right. Another way to write the same thing is that the change in the, I'll write it as the change in the kinetic energy plus the change in the electric potential energy. Should do this as like that. Those all add up to be 0, right? Does anyone need me to go through why that works out? Because if the energy is constant, if you don't lose or gain energy, the system, all right? All right, so we now know this is a number, right? We know that this is equal to this, okay? So I'm just gonna kind of push this over here and we get the delta KE equals, be careful, right? Minus, right? Oh, sorry, this was the, yeah, minus 8. And that'd be joules. What's your formula for kinetic energy again? We came up with a final minus the initial, final minus the initial. Well, we have a negative sign hanging around here, so let's check that later. Times 10 to the negative 16 joules. All right, so now what is this, the velocity? Yep. So now we have to solve for v squared. What was the mass of an electron? 9.31 times 10 to the, is it just 9.1? And that'd be kilograms. Now remember, to undo a squared term, you got to take the square root of both sides. So square root of both sides, square root of this, square root of that, and that's going to just be v. What did that work out to be?
4.2 times 10 to the power 7.
Power 7? Okay, that still works. We actually, believe it or not, for this one's fine. It's not fast enough to take into account. Did you guys do relativity in first semester or DP1? No. Okay, I think we do that in an ATL this year. But like, oh, and this should be meters per second, right? But when things go very, very, very fast, like approaching this speed, you have to take into account relativity.
So wait, is that near light speed?
So light speed is about 3 times 10 to the 8th meters per second. So yeah, we'd have to actually, believe it or not. So this is like a ballpark, but like we have to take into account relativity. That's the speed of light, 3 times in a vacuum. Okay, so we'd actually have to take into account relativistic effects, believe it or not.
Like what?
Well,
Like time slowing?
yeah, well, time would slow down, but like also the closer to the speed of light that you approach, the more energy is required to get there. So like, could this actually do that? Probably not, in reality. Then there was one, did anyone look at number 2? Anyone look at number 2? Okay, so number 2 said, sorry, does anyone still need that? Can I read? All right, number 2 said a thundercloud typically developed voltage differences of about 10 to the 8th or 10 to the 8th volts. Given that an electric field of 3 times 10 to the 6 volts per meter is required to produce an electric spark within a volume of air, estimate the length of the lightning bolt. So, so can I erase this? One of the biggest things in terms of solving problems, try to draw a picture. So like if you look at a problem, you're like, I have no idea how to do that. Try to draw a picture, a diagram, and label the things that you know. So like if you imagine this, you have like a cloud, and what we want to know is like, you have like some bolt of lightning, right? And what do we say here? So the potential difference between this point and the ground, that's what, 10 to the 8th? What else did they tell you? They said the electric field is at 3 times 10 to the 6th. Here's what I would like you guys to do right now. So I gave you guys 2 equations, right? So we said this. So we said this, Q delta V. What was the other way we could write this? Do you guys remember? So yeah, so work equals QE, so D being the distance. So notice this doesn't tell us anything about distance, right? But this one does. Remember, work is a measure of energy. This is a measure of energy. So the cool thing is when you have 2 terms that relate energy, you can set them equal to each other. So I can say, so this is work, not weight. Okay. So then Q delta V equals Q, the charge. Like we don't know what the charge is, right? No idea what the charge is. We can actually figure that out though, but we don't need it because like the unit of charge cancels with this unit of charge. Okay. We know the field strength, the electric field strength. Okay. This is one of the classes we did together. We call this the electric breakdown of air. Any voltage close to or exceeding this, assuming it's dry air, like not humid, like you're going to have sparks flying through the air. Okay. So we now have voltage difference, field strength times distance. Okay. So to figure out like how big of a distance for a spark to travel, or in this case, a lightning bolt, which is a really big spark, we don't memorize this, memorize how to do this, okay? But the distance that spark would jump, or bolt of lightning, would be like that. And then what do we say? So delta V in this case was 10 to the 8 volts. This is 3 times 10 to the 8. Can you guys tell me what this works out to be as a number? Volts per meter. Notice that the units of the volts will cancel. This unit kind of flips up. Can you guys tell me what that works out to be? This is a 10 to the 8th, 10 to the 8th. $33.333. So like, let's just say this, how many sig figs here? How many sig figs do I have? 2? I have 1. So like, so this is just to reiterate, to reemphasize a point. If you, in your calculator, if you get, would you say like 33.333, because this is like 1/3, right? Yeah. You only have 1 sig fig, so what should the actual number be? 30 meters, okay? 30 meters? Yeah, so like in your calculator, it'd be like 33.3333. But remember, we only have 1 significant figure. Like, this is 1 sig fig, 1 sig fig. Right? So in your calculations, like your most accurate number is the number closest to the least sig fig.
So if you're saying 3.0 times 10 to the power 6, so the answer would be 34 meters.
If you said, yeah, if you said like 3.0, but in this case, like, we didn't put the 0.
Okay.
For my purposes, like for us in class, if you guys wrote this, if this was like a quiz, I'd be like, cool, you got the right answer. But if it was like, if you're taking a standardized test, they'd want to see like this. They might put this as like a distractor to like be like, you know, like a standardized test might put these two things, and they would only give you credit for like circling that one. If they wrote like 3.0, then like, yeah, like you could do like 2 sig figs and maybe make that 33. All right, Cece, did your hand go up? No? Okay, questions on these? All right, I hate these type of questions mainly because, you know, there's no practical application to this. So let's actually get into a practical application. All right, and so we're gonna start electric circuits. And I have a question for you. Don't yell out an answer. If I have a ball on an inclined plane, Annie, can you put the ruler down? And there you go. I can get you like a screw. Wait, here, do you want to? You can squeeze this thing if you want. You need something? No? There you go. Oh, that'll be loud though. Yeah. That's like nails on a chalkboard. All right, so check it out. This sounds like a silly question. If you put a ball on an inclined plane or anything round or on a hill, why does it roll down? Don't say gravity. Why does it roll down? It misses the ground, but it's touching the ground. Well, friction keeps it from sliding. So like,
Why does it roll down?
yeah, why does it, I don't want to say fall down, like, because like,
Angle. Yeah.
potential energy, there. Yeah, so like, here's the analogy that I'm going to try to make. Like, all right, so imagine this is like the inside of a wire. So this is a ball on an inclined plane or a hill, and you have like an electron right here. Why if I hook this up to a battery or plug it into a wall, why will the electron actually move through the wire? Okay. Well, not conductivity. The answer is actually, believe it or not, the same here. Like you have a high potential. And okay, because I'm being lazy right now, I'm gonna just write high potential energy, okay? So you have a ball that's on a hill, it has high potential energy. At the bottom of the hill, it has low potential energy. So you can get things to move. Believe it or not, energy is kind of like a made up concept. I don't know if you guys talked about that, but like energy, like we don't like to talk about energy a lot because it's kind of like bookkeeping. It happens to work out. It makes hard problems easy. So the ball is going to roll down the hill because you go from high potential energy to low potential energy. Nature is always trying to be in its lowest energy configuration possible. That's why things kind of do what they do. So in a wire, if you hook the wire up to a battery, you have electrons. They're going to move from high electric potential energy or high voltage. I'm going to just write this as voltage for now, which is high potential energy, to low potential energy. All right, the thing that always confuses people, if I take this wire now and I reorientate it so that now the wire looks like this, and the electron moves that way, and say, where is it higher in potential energy? Well, it's the same thing here. I just took this wire and I went like this, so it's got to be high potential energy here. All right, low V, okay? That's an important concept, okay? It seems simple to look at, but like we need to know why electrons will move through a wire if we hook it up to a battery. All right. Did you guys in a previous class see the symbol for a battery? Yeah. So like if I drew this, you knew like this is a battery. Like yeah. There are two different symbols. Like if you get into engineering, you'll see that for some reason, like we draw batteries that look like this. Okay. And then like there's actually one more step I want to do. If we make a simple circuit, what's this a symbol for? You guys remember? Yeah, resistor. So like, remember this is a resistor. I don't recommend doing this, but has anyone ever taken a battery, taken just the wire by itself, hooked it up? What happens to the battery? Yeah, first it heats up because like you essentially have no resistance, and that chemical reaction taking place within the battery is happening so fast, it's creating internal friction. It's going to heat up. It's going to cause those atoms to move faster, and eventually it's going to pop, which you don't want to get battery acid on you. Now, if I start to add resistors to my circuit, what's the independent variable? Is voltage independent of current, or is current independent of voltage? Which one is which? Do you have a current without a voltage? No, so which one's dependent, or which one's independent, I should say? Voltage. So if I create a graph where voltage is on this axis, voltage, and current is on this axis, what does this graph look like, assuming like ideal conditions? Does anyone know? Like, so look something like this. All right, here's the important part that you need to know. This is true only for things we call ohmic. All right, most things are not ohmic. All right, so like if you look at a light bulb, like not these fluorescent lights, but they operate differently. A light bulb looks something like this. Like if you were to graph, like if you were to hook up a light bulb to a battery and slowly start turning up the current, or the voltage, I should say, like this is what this is a light bulb. Light bulbs are not ohmic, okay? They do not follow what we call Ohm's law. Does anyone remember what Ohm's law is? Voltage equals something times current. You guys remember that formula?
Resistance.
Yep, so voltage equals current. I'm going to say resistance times current. All right, so know this, like this is super important for electric circuits. Ohm's law, so this is Ohm's law. Your book, I don't think names it, but know the name. This is like probably one of the best ones to know in the book. So we just write that as V equals IR. So know this law, voltage. Voltage equals IR. Current times resistance.
What is current? I.
Probably something from the Latin, I forget exactly. It's a good question, and like I think your book might use a capital I because that stood for the conventional current. So back before we knew that there were these things in a wire called atoms, and we used to think that it was like positive charges that moved through the wire. We now know it's the negative charges. All right, so what I want to do is come up with a couple of rules and just, what time is it? All right, it's cool, we got a couple minutes. Yeah, Ohm's law, Ohm's law. All right, so what I'd like you to do, draw this circuit, and who is HL in here? Who's HL? Okay, cool. All right. Normally when I teach electric circuits, I teach you resistance or resistor circuits and capacitor circuits at the exact same time, but not everyone needs to know about like capacitors. So like for people who are doing HL, I want you to make sure that you save these notes, because when we start talking about capacitors, like, you know, like in the in the spring, like when we're doing electromagnetic induction, you really need this stuff. All right, but check it out. So I'm going to draw my batteries like this, and the reason I'm bringing this up is there's this other circuit element that looks just like this, which if I draw that in my battery, like sometimes they kind of tend to look alike. So I use like an American battery, if you will. It's the same thing. Let's say, so I'm gonna just like keep numbers easy for today. Like, so let's say I have a 10-volt battery. All right, some important things. Do you remember, like, just in terms of like doing circuits, what side is like positive, which side is negative? So top, right? So like sometimes we do this, sometimes we put a little minus there, okay? Because we like to think one side is positive relative to the other. Which way is the current going to flow out of this circuit? Which way is the current going to flow? Yeah, so we're going to draw it like this. And I'm not like, all right. So like there's this thing called conventional current and there's this thing called electron current. Let's not make a distinction between the two right now because believe it or not, it all works out except for the sign of things. We'll talk about that when we need to. Now let me ask you this. If you have 10 volts going, or if you have 10 volts between the two batteries or between the terminals of the battery, one way to think of that is let's call this point A. Let's call this point B. So one way to think of this is point A has 10 volts. What would that make point B? If point A is 10 volts, it's like the top of the battery, what would point B be? Well, if both sides was 10 volts,
Then we have negative.
well, would the battery even work? So like, what do you think this one has to be?
Nice.
Well, let's call it 0 volts. Okay.
What would be 0 volts?
Well, let me ask you a slightly different question. So like, I'm going to ask a parallel question. Imagine like you're holding a ball or something like that. Where is the potential energy 0? Here or here? Could be either, right? It doesn't matter, believe it or not. Like I could say that my height right here, and if I want to solve the problem, I could say that this is height, this is my height, and I can call it 0. And whatever this is, however far this falls, let's call it D. Like, how about this? Let's just call it minus 10 meters. I could say that, or like, and so I could call this minus 10. Actually, let's just get rid of the minus here so I can put it here. I could use the same set of equations, and I could call this B like 0, and I could call this 10. It doesn't really matter, believe it or not, because like conservation of energy lets us ignore signs for the most part. All right, so here's my question. What's the voltage across here? So like if you want to think of it, if you want to think of this as, let's draw this as a set of stairs. So what a battery does is it gives electrons energy, okay? Or it creates a potential difference. And what that does is if you imagine here's an electron, this is your battery. Your battery increases the energy of the electrons. How much? Well, it depends on the size of the battery. Is it a 5-volt battery, 10-volt battery, 100-volt battery? The greater the voltage of the battery, the more energy each electron has. And then what happens here, the resistor uses up that energy, okay? That's why your battery doesn't heat up so much and explode on you. So like a resistor is kind of like does the opposite. A resistor uses up the energy. So if you want to think of this battery as a set of stairs that gives the electron energy, well, then you're going to have a voltage increase. And then what the resistor does is it drops the voltage. So you have a change in voltage. Basically, you're going, the battery takes you up the stairs, the resistor brings you down the stairs, okay? So across a resistor, you have a voltage drop. How much? Well, it depends on what the voltage of the battery is, okay? So this is a simple circuit. This does not do much. This is like a light bulb, right? That's all this thing is. It doesn't do anything useful other than keep a light bulb from having too much current. So I'd like to look at the next step. Oh, hold on. There is one. Let's do one simple problem. Let's say that this is a 100 ohm resistor. So let's call this R1. So the unit that we use to measure resistance is called the ohm. Imagine like you're drawing a stick figure with like big feet. Imagine that's your stick figure. The symbol for the ohm is basically just the legs. Okay, so this is called the ohm, OHM, like that. Measures resistance. That's our unit used to measure resistance. Here's my question for you. You know the voltage, you know the resistance. Figure out what the current is. So find the current, please. We have 4 minutes. Let's just work out what's 10 divided by 100. 0.1. What are the units for? What are the units for current? Amperes. Good. So
0.1 or 0.1?
0.1, right? So the ampere. So here are a few names for current. So current could either be ampere, amps, or just capital A. All right, all are equally valid. We only have like 3 minutes left. All right, so check it out. What I'm going to do is I'm going to put some homework. Is everyone now on InThink? Everyone's able to access InThink? All right, so I'm going to put a few problems on InThink to do voltage and maybe a few electric circuit ones. Maybe not, because like this is not even a real problem. It's simple. Next week on Tuesday, we're going to start to do real circuit analysis. We'll figure out all of the current laws and all of the voltage laws, and we'll pick it up from there. Cool? All right. So Olivia, I'll see you Tuesday.